Okay.
Got it.
Welcome everybody to the Santa Barbara Astronomical Unit's public meeting for the first Friday of June, June 3rd. We are slowly approaching reopening these meetings to live meetings in Ferrand Hall. And we're just waiting for the COVID to at least slow its advance so we can do that. There'll be more on that next week after we have our business meeting. You'll hear about that at the first meeting in July. But I just want to make a few or ask before we start. I introduce the vice president who will introduce our speaker. If Chuck has any announcements on outreach that you'd like to make.
Well, we're getting busy again. We have Refugio State Beach tomorrow night, likely to be a little cloudy, but we'll see. And then Telescope Tuesday on the 7th, the first Tuesday of each month at a commuter rail marketplace. Another Refugio State Beach on Friday the 10th. And then the second Saturday Star Party at the museum on the 11th on Saturday. We're going to start that at 8:30 since sunset is so much later. And then on Wednesday the 15th, we have another Refugio. Refugio is hitting us hard this month. And then third Friday at Westmont on the 17th. And then on the 18th, Carpinteria State Beach is starting up again. And then on the 23rd, another Refugio State Beach. And on the 25th, another Carpinteria State Beach. So the state beaches are picking up activity. Next month, Cachuma will be grabbing a bunch of Saturdays. So We're starting up again.
Good news. Thank you, Chuck.
Yeah, you're welcome.
Okay. So I think that we'll save the business of the business meeting and we'll go right to our vice president who will introduce tonight's speaker.
You know, when I go to Chrissy, she's here, she's with us. Chrissy Cook, do you have anything real quick to say?
Just hello and greetings from the Natural History Museum. We're all happy you're here. I'm excited and looking forward to our evening.
Well, I'm going to plug real quickly our Monday morning blog podcast, which is going to have episode 67 this coming Monday morning. Many of the same faces you see on the screen will be on board 11 to noon, and you can see it on YouTube again. Ladies and gentlemen, we got a good one this time. Our guest speaker for the merry month of June is a postdoctoral scholar for the Cahill Center for Astrophysics down at California Institute of Technology. The man got his master's degree in physics from Sharif University of Technology in Tehran, Iran, back in 2009. Then received his PhD in physics and astronomy from the University of California, Riverside in 2015. He was a postdoctoral scholar at Caltech from 2015 to 2022. And recently, Dr. Ben began a position as project scientist at UC Riverside, at the same time a visiting scholar at Caltech since February of this year. And I want to thank Joe Doyle, who met our guest speaker at Mount Pinos at a recent event. Maybe someday we'll find out what that was all about. Ladies and gentlemen, please be ready for an incredible show or a program on the growth of galaxies over eons with, from Caltech, Dr. Ben Darvish. Ben, live from his home.
Hi, thank you for your great introduction. I was looking forward to attending this event for tonight. So I want to go ahead and share my slides with you guys slide and start the talk here.
What's the name of your talk, Doctor?
It's about the role of environment in the evolution of galaxies.
There you go. There you go. Evolution of galaxies in diverse environments.
Yeah. So share screen and all right. Can you see my slides here?
Yep. See something.
Wonderful. All right. You see something right now?
Yep.
Great.
I do.
So,
rest of you? Okay.
Today, I wanted to thank you again for inviting me and for the great introduction, Ron. Today, I want to talk about the role of galaxy environments and cosmic web on the evolution of galaxies over a broad cosmic time. All right, I'll start my talk with some fundamental questions here. And during my talk, I'll try to address some of these and discuss them. What do you mean, the first question, what do we mean by the environment of galaxies? What do you mean when we talk about the environment of galaxies? How can we define the environment of galaxies, and how can we characterize the environment of galaxies? And after characterizing and defining the environment of galaxies, we're interested in knowing the potential relation between a galaxy's environment and its physical properties, in particular, the level of star formation activity in galaxies. We will address and discuss the important question of what has or have caused the star formation activity to stop, or in technical terms, to quench in galaxies. We would like to know the fractional role of nurture or a galaxy's environment and the internal processes in galaxies in stopping or quenching the star formation activity in them. How about the bursting of star formation in galaxies? Where does the bursting of star formation activity in galaxies sit in this picture that we will draw? We're interested in knowing whether the environmental effects, if any, are basically either whether they're a local phenomena or act on much larger physical scales of the cosmic web as well. I'll get to this point in a minute. And finally, what is the potential role of the cosmic web, especially galaxy filaments in the evolution of galaxies, which is currently a very new hot topic in the field. I'll start with some definitions here. You may already know some of these, but I'll go over them very quickly as a recap. Parsec is a measure of distance that we commonly use. Here, I'll use megaparsec or million parsec here, given the sizes that I'm dealing with in this case. 1 megaparsec or million parsec is about 3.26 million light years. Redshift, I will commonly use that, is a measure of distance, also a measure of look back time, and a measure of how fast galaxies are moving away from us because of the expansion of the universe. And the reason why we use redshift a lot is because that's a quantity that is directly measurable in astronomy. Some examples here, the Virgo cluster, for example, is at redshift of 0.004. It's a nearby galaxy cluster, which corresponds to a distance of about 16 megaparsec. A look back time of around 53 million years. It means it takes about 53 million years for the light of galaxies in the Virgo cluster to reach us. And rotational velocity, because of the expansion of the universe, of about 1,000 kilometers per second. I want you to remember this for an object that is at redshift of around, say, 0.8, 0.1, that corresponds to a distance of about, say, 3,000 million parsecs. And a look back time of about 7 billion years. And given the age of the universe, when we talk about a galaxy or an object that is at redshift of around 1, we're talking about like half of the universe, half of the age of the universe. So look back time of about 7 billion years. And at redshift of 2, that corresponds to a distance of about 5,000 megaparsecs and a look back time of about 10.4 billion years, which is like just a few billion years after the Big Bang. I want you to just remember these numbers because we'll get to these in a minute. What is a spectroscopic redshift? A spectroscopic redshift is a way of, the most accurate way of determining the redshifts of galaxies or objects in the universe. And for that purpose, we use spectrographs. And what we do is that we look at some characteristic emission or absorption features, say Lyman H alpha line, Lyman alpha line, H beta line, oxygen 3, calcium H and K, and so on. And we see by how much they are redshifted to longer wavelengths because of the expansion of the universe. As simple as that. Let me give you an example. For example, H alpha emission. You either use H alpha narrowbands for imaging or oxygen 3 filters for visual stuff. So the lab wavelengths of H alpha line is at 65, 64 angstroms. But for a galaxy that is at redshift of, say, Z, and this is the lab wavelengths of H alpha line is in the optical or red region of the spectrum. But for a galaxy that is at redshift of Z, this line is not in the red part of the spectrum anymore. It's redshifted toward longer wavelengths. And to estimate that, you need to simply multiply the lab wavelengths of, say, H alpha by 1 plus redshift of that object. Say if you have an object has redshift of 2, 2 plus 1, 3 times 65, 64, we end up with something like 20,000 angstrom, which is in near IR part of the spectrum right now. And I'll get to that in near future here. So a spectroscopic redshift is therefore the most accurate way of determining redshift for galaxies, but it's only possible, it's very slow to take. It takes time, time consuming, and it's only available for a small subsample of galaxies in a large galaxy survey, typically a few % of the galaxies. Therefore, we rely on photometry to estimate redshift of galaxies, and that's called photometric redshifts. For that, we do imaging in multiple filters or bands, and because of that, although it's less reliable compared to spectroscopic redshifts, but this is very cheap. Imaging is very cheap compared to spectroscopy. It's cheap, it's fast to obtain, and can be obtained for a large sample of galaxies in a galaxy survey. Magnitude, you already know that, the measure of brightness. Color, we define that as a magnitude difference in, say, 2 bands, say B band, R band, we can define color. A higher value of color means the object is redder. A lower value of that means the object is bluer. Metallicity is the abundance of elements heavier than helium that we use commonly in astronomy. Galaxy clusters are basically massive gravitationally bound systems with many galaxies, gas particles, and dark matter particles that are held together through their mutual gravity. And typically they have total masses of something like 10 to the 14 to 10 to the 15 solar masses. An example, the Coma cluster. Galaxy groups are less massive gravitational bound systems that have typically masses of 10 to the 11 to 10 to 12 to 10 to 14 solar masses. Examples are local group of galaxies or Leo triplet galaxy group. Field galaxies. When we talk about field galaxies, we mean galaxies that do not belong to dense environments like galaxy groups or galaxy clusters. They're basically isolated galaxies. Central galaxies, the most massive or brightest galaxy in a galaxy cluster or galaxy group is defined as a central galaxy, and the rest of the galaxies are defined as satellite galaxies. So in order to do science, we need to start with some data. So as a member of the Cosmos survey, I had the opportunity to use their incredible data set, and I'll get to that. The Cosmos Field Survey is a large galaxy survey covering about 2 square degrees in the constellation Sextant. It's an equatorial field, and the reason why it's selected to be equatorial because we want it to be observable from both hemispheres, observatories from both hemispheres. In fact, this is the largest contiguous galaxy survey that has ever been done with the Hubble Space Telescope, and one of the deepest of the surveys that has ever been done by the HST. The power of the Cosmos survey relies on 2 things. It's aerial coverage and also its wavelengths coverage. The wavelengths coverage goes from X-ray to the radio waves. That has been done with all the major space and ground-based telescopes. I'll give you some examples. In X-ray, we have XMM Newton and Chandra Space Telescope that has observed this region. In UV, Galaxy Space Telescope has observed this region and some HST data. In optical, we have Hubble Space Telescope, Keck, VLT, Subaru, CFHD, and so on. In near IR, HST has covered that area, Vista Telescope, CFHD, UCURT, and many more. In mid IR, we have Spitzer Space Telescope that has covered this region. Far IR, Herschel Space Telescope, sub-millimeter, we have ALMA pointings in the Cosmos field. In radio, we have VLA data from radio arrays. So we have a huge wavelength coverage. We detected 2 million galaxies in this small region of the sky. And we have reliable photometric redshift measurements for all these 2 million galaxies, up to redshift of 3, which covers about like 75% of the age of the universe. And we have a spectroscopic redshifts available for around 20,000 of these galaxies, which is about like 1% of the total number of detected galaxies. And in near future, this field will be observed by James Webb Space Telescope, Euclid Space Telescope, Roman Space Telescope, LSST, and so on. So with this data set, we can do a lot of science. So I'll start with the first question. How can we define the environment of galaxies? In order to do that, I had two approaches here. In the first approach, I use the overdensity of galaxies as a measure of their environment. And by overdensity, I mean how crowded is the immediate neighborhood of a galaxy. If a galaxy has a higher overdensity value, it means it's located in a more crowded environment. And if it has a lower overdensity value, means it's the neighborhood of that is not as crowded, basically. How can we do that? I'll give you an example, everyday example. We've all seen weather forecasts, this figure, for example, here, weather forecast maps. What they do is that we have some discrete weather stations, say across the US, and we take measurements of the temperature. And we go from some discrete points of temperature measurements across the US and make a continuous heat map, for example. This is what we're trying to do. Here we go from a discrete points of galaxies in space and try to something that we call the overdensity maps. And we have denser regions, for example, I color them with red color, right? Denser regions and blue regions that are less crowded or less dense. So we make something and call it overdensity and make overdensity maps. And we use that overdensity value as a measure of the local environment of galaxies. And this is a real example of the Cosmos data. It's galaxies at redshift of around 0.9. And this is the overdensity map that we made based upon with this distribution of galaxies. That's one way of defining the environment of galaxies. And the second part of my talk, I'll define the environment as components of the cosmic web. Cosmic web and its components that are galaxy filaments, galaxy clusters, and field or voids on much larger physical scales. What is the cosmic web? So galaxies on large scales are not distributed randomly in space. Rather, they form a network known as the cosmic web. This network has some dense regions that we call them galaxy clusters and galaxy groups that are woven together by thread or filament-like structures that we call them filaments. They're not just randomly distributed. Let me give you two examples. The figure on the left side, this is from Millennium simulation that shows that at redshift of 0 shows the distribution of dark matter particles. Dark matter particles are not randomly distributed. They form a network. Denser regions here are galaxy clusters that are woven together by filaments of dark matter particles. We've seen the same for real galaxies. On the right side, I'm showing the distribution of galaxies from the SDSS galaxy survey between redshift of 0 and 0.14. And again, they're not just randomly distributed. They form a network of cosmic web. Denser regions are galaxy clusters and groups that are connected together through filaments of galaxies. So we use the overdensity of galaxies as a measure of their environment. We need to develop tools in order to do that. And let me remind you, it's more complicated than the weather forecast maps that I mentioned before. Why? Because although we very accurately know the position of galaxies, I mean, right ascension and declinations of them. Is there a question?
Yeah, I would like you. Did I hear you say that dark matter follows the same web?
Yeah. They basically, if you look at the distribution of dark matter particles, they follow the same shape.
Okay. Thank you.
You're welcome. So we need to have a tool, and as I mentioned, it's more complicated than weather forecast, basically weather maps that we've seen, because although we accurately know the right ascension and declination of galaxies, what we do not know very accurately is the redshifts of them. We rely on the photometric redshifts of galaxies, which is the third dimension, and there are uncertainties to them. Remember, spectroscopic redshifts are only available for 1% of galaxies. And in order to do science, we rely on photometric redshifts here. Because of that, that's the complexity that arises here. Therefore, we need to have a statistical approach to this problem, like a probabilistic approach to that. For that purpose, we develop different methods and algorithms. And in order to pick the best algorithm or method that allows us to find the overdensity of galaxies, we perform extensive computer simulations to pick the best method. And then from those methods, we found the best one of them and then applied that to all 2 million galaxies in the cosmos field. to end up with a reliable overdensity value for them up to redshift of 3, which covers about 11 billion years of cosmic time. Okay, the figure on the top left side is basically the overall projected overdensity of galaxies in the cosmos field between redshift 0.1 and 3, covering about 11 billion years of cosmic time. The red regions are very dense environments, of course, and green and blue ones are less dense ones. Remember, this is based on our method, and we use photometric redshifts with uncertainties in them. In order to make sure that these dense structures are real, we need to do, for example, follow-up spectroscopy. And in fact, we've done that. Some of these studies by our own group, some of them by others. And I'm labeling some of these structures that have been confirmed spectroscopically. For example, one structure, biggest structure at redshift 0.7, one at 2.45. And it means that we're good, right? The method that we develop is able to generate reliable maps. Are there other indicators? Of course, look at this figure in the bottom left side. Whenever we have a concentration of galaxies, we also expect to have a concentration of gas. And in fact, the environment of galaxy clusters and some galaxy groups is filled with very hot gas that emits X-ray emission. Therefore, if you look at the X-ray emission and generate a map like this, is based on a paper from 2007 using XMM Newton data, we expect to see a concentration of hot gas that should correspond to concentration of galaxies. And we found a very good one-to-one agreement between what we found and what we can see in X-ray. Are there other indicators as well? Of course, whenever you have concentration of galaxies, you expect to have concentration of hot gas and concentration of dark matter particles. We can look at the shape of the galaxy and use a technique known as weak lensing to look at the overall total matter distribution. For example, the cosmos field dominated by dark matter. This has been done by these papers, in Nature paper 2007. And again, we see that the concentration of dark matter corresponds to concentration of hot gas and corresponds to the map that we only generated based on photometric redshifts of galaxies. We're good to go. It's time to celebrate, right? And it's just the beginning to do science. Now we believe that we have developed a reliable tool that allows us to quantify the environment of galaxies, and that is the overdensity of galaxies. We are interested in knowing the role of the environment in the level of star formation activity in galaxies. This is a very, very important topic in astronomy. We want to know what has caused the star formation activity to stop in galaxies. This is known as galaxy quenching. Let me give you some observational facts. We know observationally that galaxies form two populations, distinct populations, on a color magnitude diagram, right? If you look at the colors of galaxies as a function of their luminosities or absolute magnitude, they form two distinct regions or populations known as red sequence and blue cloud. And in between them, we have some galaxies. In transition galaxies, we call them green valley galaxies. This is based on, I took it from Wikipedia, but the bottom figure is based on real data. It's SDSS, about 300,000 galaxies from SDSS and UV galaxy surveys. And again, we clearly see two distinct populations of galaxies, red sequence galaxies and blue cloud galaxies in the color magnitude diagram, basically. Red sequence galaxies are mostly red. They're elliptical galaxies mostly with little to no star formation activity in them. And on the other side, blue cloud galaxies are mostly blue. They have a lot of star formation activity going on in them, and they're mostly spiral galaxies, okay? We are interested to know what has caused the blue cloud star-forming galaxies to stop forming stars and migrate to the red sequence, which is basically dominated by dead, passive, red, inactive galaxies. This is known as quenching. What has caused the star formation activity to stop in galaxies? If you are a theorist, you want to propose a model for the formation of galaxies, you got to be able to describe this bimodality in galaxy colors. This is a very important observational fact that we know. How is that related to our talk? Let me give you another background. Studies in the local universe, say less than redshift 0.3, thanks to large surveys in the local universe like SDSS survey and gamma survey. From these studies, observationally, we know two important facts. The first one is that we know that galaxy clusters and denser environments are dominated by passive, red, and mostly elliptical galaxies, again, with little to no star formation activity. Therefore, maybe the reason why galaxies stop forming stars and migrate from the blue cloud to the red sequence has something to do with galaxy clusters and denser environments. Okay. The other important observational discovery that we know, observational fact from nearby studies, is that also we know that on average, more massive galaxies are redder, again, less star forming and more likely to have elliptical morphologies. Therefore, there is something related to the internal properties of galaxies that is related to the stellar mass of galaxies that has the potential to stop the star formation activity in them, making them dead, quench, passive, and red. Because of these discoveries, based on nearby large studies in the nearby universe, two general quenching mechanisms have been proposed observationally. Environmental quenching mechanism, something to do with environment that has the ability to quench galaxies, and mass quenching environments. Something is going on that is related to the mass of galaxies is going on in galaxies that has the ability to quench them. Regardless of the physics of them. The picture, I talked about nearby universe studies. The picture is not clear as we go to intermediate and high redshifts, say redshifts greater than 1. Yes.
Is there, this may be a little off the topic, I hope not, but is there a difference between elliptical galaxies and spiral galaxies in the rate of nova and supernova? That is, if the elliptical galaxies are absent dust, and the source of their dust is novas and supernovas, does that show up in black?
So supernova are byproduct of basically massive stars, right? And yeah. I guess we expect to see more of them in spiral galaxies. They're active in forming stars than dead, passive red galaxies, elliptical galaxies that have almost no gas and dust to form any kind of star formation activity. So about the questions, I'd rather
Chuck has the questions too.
Yeah, and there seems to be an age difference there too then when we talk about them migrating from one to the other. So the ellipticals are older, and being older, if they're not forming stars, they wouldn't have massive stars that would blow up in supernovae.
Yeah, exactly. The age difference is another factor involved. So can we have questions at the end of the talk? I think it would be better. I'd rather have that. It's okay with you guys. All right. I mentioned about elliptical galaxies being and passive dead galaxies being more common in denser environments. And this is a real example. Look at the Coma cluster. Most of these galaxies are red, dead, passive galaxies, elliptical galaxies with little to no star formation activity. This is an example of a field galaxy, isolated galaxy, active in forming stars, spiral galaxy, right? So I didn't talk about the physics in these that is related to either environmental quenching or mass quenching. If you are a theorist or computational astrophysicist, you're interested to know the physics behind it, right? And many physical mechanisms have been proposed that are either related to galaxy clusters or related to the stellar mass of galaxies. Let me go over that. To form stars, you need to have some gas. This gas needs to be cold, typically hydrogen in molecular form, and there is often dust present in the environment. On the other side, if you want to stop star formation activity or quench galaxies, all you need to do is to either physically remove the gas available for galaxies, shut off their gas supply, heat up the gas to stop forming stars, or somehow consume the gas available for galaxies over a short period of time. So any physical mechanism that can do any of these or a combination of these has the potential to quench galaxies. Some of them that are related to the environment of galaxies and that can happen, for example, in galaxy clusters, these physical mechanisms have been proposed. Many of them, like we have ramp pressure stripping, galaxy-galaxy interactions, strangulation, galaxy cluster tidal interactions, and so on. Let me give you one example. For example, ramp pressure stripping. What is ramp pressure stripping? It's just the a drag force that galaxies feel as they enter the hot, harsh, dense environment of galaxies. This drag force causes the gas and dust in the galaxies to get basically stripped. The result of that is the shut off the star formation activity in galaxies. I'll give you two examples here. This is galaxy NGC 4402. It's part of the Markarian chain, and it's very close to M84 in the Virgo cluster. The green arrow shows the direction of the motion of the galaxy toward the center of the Virgo cluster. And if you look at carefully look at the shape of the galaxy, it's bow-shaped like this, because it's feeling a ramp pressure that is acting in the opposite direction that is causing the shape of the galaxy to look like a bow. And also, we see that the gas of this galaxy and dust planes form like a tail behind the galaxy because of that. Another example is galaxy NGC 4569, again in the Virgo cluster. It's in the process of being stripped by the ramp pressure of the Virgo environment. So as I mentioned, there are some physical mechanisms that are related to the environment of galaxies, and there are also some physical mechanisms that are related somehow to the stellar mass of galaxies that have the potential to quench them. Some of them, like feedback from supermassive black hole at the center of galaxies, they can either heat up the gas or mechanically remove the gas from the galaxies. Supernova explosions have the power to do that, and stellar winds from very young stars. These are related to the mass, all of them related to the mass of galaxies. A beautiful example of that is a galaxy, we've all seen that, either visually or taken pictures of that, whatever. Galaxy M82, right? If you take narrowband data of this galaxy, we see that there are two lobes of hot ionized hydrogen gas kind of coming perpendicular in two opposite directions from the disk of this galaxy, from the center of that. It's been shown that part of this is due to supernova explosions, stellar winds, and some contribution from the supermassive black hole feedback at the center of this galaxy. Again, regardless of the physics as an observer, we are interested to know how environmental quenching and mass quenching, regardless of their physics, have the ability to quench galaxies. As I mentioned again, this picture is not very clear at intermediate and high redshifts. Therefore, we need to have data set like that of the cosmos field that allows us to do this study. I'll give you an example here. It's based on a paper I published in 2016, and we had a press release about that. We found a number of interesting results regarding environmental quenching and mass quenching. We defined two simple parameters. We defined environmental quenching efficiency as the ability of the environment to quench galaxies, and mass quenching efficiency similarly as the ability of the physical mechanisms related to the stellar mass of galaxies to quench them, right? For that purpose, we used 200,000 galaxies spanning 10 billion years of cosmic time in the cosmos field. A look at the figure on the left side. This, for example, shows the environmental quenching efficiency, the ability of the environment to quench galaxies as a function of redshift. Higher redshifts, lower redshifts. We see two important trends here. First off, we see that over time, as time progresses, the ability of the environment in quenching galaxies increases with cosmic time. In other words, environment becomes more powerful in stopping star formation activity as we get to lower and lower redshifts. And we see the other things. The ability of the environment in quenching galaxies is more efficient on more massive galaxies. I'm showing them with red points here than less massive galaxies than blue points here. We see the same thing. If we can do the same exercise with mass quenching efficiency, we see similar results. Mass quenching efficiency becomes more efficient with cosmic time, and it's more efficient in denser environments than less dense environments. And because of these similarities, we found some interesting results here, conclusions. First off, mass and environmental quenchings go hand in hand in quenching the star formation activity in galaxies. They're not independent processes. And because of the similarities that we found here, maybe mass quenching and environmental quenching originate actually from the same physics that have been basically reflected into two apparently different things. And if you are a theorist, you've got to consider that, right? You've got to choose a model that is able to describe these observations, basically. We also found another interesting result that I'm showing here, for example, in these figures. Let me just describe the result that we found. We found that at higher redshifts, say redshifts greater than 1, mass quenching mechanism is the dominant mechanism for quenching, regardless of the nature of that. And as we get to lower and lower redshifts, the environment starts to catch up. And say below redshift of 1, it even dominates the mass quenching mechanism. So at higher redshifts, mass quenching is a dominant thing that stops star formation activity in galaxies. Lower redshifts, likely denser environments. Again, if you're a theorist, take this into account in your model and see which one can describe these observations. I kept talking about quenching of galaxies, the cessation of star formation activity in galaxies. But galaxies can also burst. The opposite of that is possible. Some galaxies may go from the red sequence to the blue clouds, right? Although we know that the overall flow is from blue cloud to the red sequence toward quenching. In fact, what is really interesting is that many of the physical quenching mechanisms that I just described may actually temporarily elevate and enhance star formation activity in galaxies prior to the full quenching of galaxies. Kind of contradictory, right? I'll give you three examples that we know of. Ramp pressure stripping. Ramp pressure stripping can temporarily, in some cases, compress the gas in galaxies. Compression of gas results in a burst of star formation activity in them, elevates the star formation activity. Galaxy-galaxy interactions that are very common in dense environments have the potential to make them dead and passive. But galaxy-galaxy interactions can cause the gas in the periphery of interacting galaxies to get compressed and funnel toward the center of that. The compression of the gas results in a starburst and also activates the supermassive black hole at their center. Elevates the star formation activity prior to quenching. Supermassive black holes can both quench galaxies and elevate star formation activity in them. I'll give you some real examples. Look at this ramp pressure stripped galaxy in the Virgo cluster. The tail that is left behind it's basically hot ionized hydrogen gas, right? We see an elevation of star formation activity in this galaxy that is being ramp pressure stripped, right? Prior to the full quenching of that. A real example, bottom figure here. We've seen, it's been shown that a supermassive black hole at this galaxy, NGC 5643, has caused the star formation activity to elevate in the disk of this galaxy. So in order to have a complete and better picture of galaxy evolution, we need to be able to simultaneously quantify both quenching and bursting of galaxies. For that purpose, we need to develop a tool. I don't want to go into details of that. This is what we did in these papers. So the purpose of developing this new tool was to first allow us to estimate the physical parameters of galaxies, say their metallicities, stellar mass, and so on. But the main purpose was that we wanted to define a new parameter, which allows us to simultaneously quantify both bursting and quenching in galaxies. I can go into details of that if you're interested, but this method that we developed is actually pretty fast compared to traditional methods. I'm talking about like minutes versus days of computational time. We applied less assumptions in the model and so on. But the main purpose was to define a new parameter. And the new parameter that we defined here, we call it star formation acceleration. And it's a very simple definition. We look at how the color of galaxies change over time. A positive star formation acceleration means that the galaxy is getting redder and redder over time or experiencing quenching. And a negative value of star formation acceleration means that the galaxy is getting bluer and bluer over time or bursting. For that, we used in the local universe STSS data set and at high redshift, of course, spectroscopic data in the cosmos field. And we found some interesting results. And I give one example here. Remember central and satellite galaxies. Central galaxies are the most massive galaxies in a cluster or a group, and satellite galaxies are the remaining galaxies in that environment. We found completely distinct behavior in centrals compared to satellites when it comes to star formation acceleration in them. The blue line is for central galaxies I'm showing here, the red line for satellite galaxies, and it's in the local universe. And we see similar trend at higher redshifts, although not that obvious compared to the local universe result. And this is the star formation acceleration.
Seems Dr. Darvish has been cut a little bit here.
We see that on average, do you hear me well right now?
Yeah, we got you back.
We lost you for 20 seconds there.
Okay, all right.
Oh, we're losing him again here. Delay.
Why is that?
Someone's running a vacuum cleaner, sucking up the data somewhere.
Ben, I guess you can't be
So,
heard. There
we go.
As you can see, I hear you well. I hear you well, but
did you hear me describe about the vacuum cleaner taking up the data?
Yes. Yes.
Okay, but you're on pause during that time. Okay.
You're locking up, and now you're okay.
Okay. Can I continue then? So
Sure.
we found that on average, central galaxies are quenchier than satellite galaxies, and we believe that's because of their location in the cluster or group environments. They're often located in the central part of clusters or groups, and that's why we call them centrals, one of the reasons. And because of that, the fresh gas supplies that can potentially act as fuel for central or satellite galaxies can hardly penetrate the central part of harsh environments of clusters. And that's why we believe centrals are quenchier than satellites. And it's actually in agreement with some recent galaxy simulations, what we found observationally. So let me move to another topic here. The density maps that we generated have the potential to find large-scale structures and protoclusters at high redshifts. Why that is important? Because currently, we only have a limited number of spectroscopically confirmed structures at high redshifts, say greater than redshift of 2. And again, more importantly, is that we have found contradictory results in the literature regarding the role of environment on the evolution of galaxies at higher redshifts. And it's partly because we have a limited sample of confirmed structures at higher redshifts. I can give you a lot of examples here about the discrepancy in the literature at high redshifts. Therefore, it's very, very important to have more and more of these discoveries. And the maps, density maps that we generated from Cosmos has the potential for these new discoveries. And I'll give you one example here, what we found. If you look at the density maps, over density maps at redshift of around 2.2, which is about, I don't know, 10.4 billion years ago, we see a huge overdensity of massive galaxies. This is based on photometry, so it needs to be confirmed spectroscopically, right? The size of that is something like 40 megaparsec by 40 megaparsec. The northern, we dug into the literature and we found the northern part of that is a confirmed protocluster that has been confirmed by another group in 2015 at redshift of 2.1. We see an overdensity at the center of that I'm showing with a question mark, and something at the southern part of that I'm labeling as this label, as this paper. This is what we went after in 2020 and confirmed that spectroscopically. Why we were interested in that part? Because we also have narrowband data in this field. And this figure shows the distribution of narrowband selected H-alpha emitter candidates at redshift of around 2.2, color-coded by their overdensity. And again, you see a huge overdensity of candidate narrowband H-alpha emitters that correspond to the southern section of this map. So we went after the densest region of that. And for that purpose, we need something, right? We use KEK, MassFire instrument on KEK. MassFire is a multi-object near IR spectrograph. Remember why we need near IR? Because if this object is at redshift of 2.2, say, and some galaxies are emitting H-alpha, H-alpha is redshifted to near IR, right? Therefore, we need to have a near IR spectrograph in order to do that. MassFire on KEK1 can do a spectroscopy on 4 IR bands, transparent bands in the atmosphere, Y, J, and H and K. It has an effective field of view of 3 arc minutes by 6 arc minutes. You can simultaneously take a spectra of maximum 46 galaxies. And we can design the mass for a spectroscopy in only a few minutes, which is a huge plus. I can talk about that later if you're interested, why that is important. You only need a few minutes to configure the mass and you're good to go for observations. And just shows me behind the primary mirror of, I guess it was KEK1. And this is the headquarters of KEK1, of the Czech Observatory in Waimea. And this shows the MassFire instrument. So as I mentioned again, we use MassFire. We did observations in H and K band, which means if the structures and objects are real, that gives us H-alpha line and some other lines in K band, and potentially oxygen 3 lines and H-beta line in H band. 1.5 hours of observations in each filter, and we designed 2 masks for spectroscopy. Observations were done under very good ideal observing conditions, no clouds, nothing. Seeing was perfect, like 0.3 to 0.4 arc seconds. And the observations were done in late 2018 and January 2019. Out of the 30 primary galaxies that we had on the mass, 29 of them yielded secure redshifts at where we expected. And also we had some feeders that gave us secure redshifts, and also we had some 3 serendipitous detections at the same redshift. There are all kinds of objects in our sample. We have star-forming galaxies, we have active galactic nuclei. Actually, 3 of them emit a strong X-ray. This is what we didn't know ahead of time. We didn't a priori went after them, but it came out to be some of them AGN. And we also ended up with some serendipitous merger detections. We have found 7 merger cases in our observations. We ended up with 35 confirmed protocluster members from our MassFire observations, and we dug into the literature and found 12 more from the Z-Cosmos spectroscopic survey in the cosmos, totaling 47 confirmed members. This is a huge number for a protocluster. Let me give you this example. If you end up with only a handful of spectroscopically confirmed members for a handful, only a few of a spectroscopic confirmation for a potential protocluster at high redshifts, that guarantees a publication, right? Now we have 47 of them confirmed. We can do a lot of science with them. I'm showing some sample spectra here. This is an H-alpha, strong H-alpha line. This is oxygen 3 line. This is H-beta line. The first 2 guys are merging galaxies. The second one is actually a beautiful triple merger, 3 galaxies that are merging together. The third one has an active galactic nuclei at the center. and the last two ones are two examples of just normal star-forming galaxies in this protocluster environment. With this huge sample that we confirm spectroscopically, therefore we can determine the physical properties of our protocluster. We estimated the centroid of that, the mean redshift to be 2.2322, and we estimated the velocity dispersion of that. You can think of the velocity dispersion as the typical velocity of galaxies in the protocluster environment. And we ended up something like 600 kilometers per second. We estimated the core size of the protocluster to be about 0.7 megaparsec. And now with the velocity dispersion and the core size, we can estimate the mass of the protocluster. And we did that with different methods. And we ended up with something like a few times 10 to the 14 solar masses. For comparison, the mass of the Virgo cluster is something like a few times 10 to the 14. And the mass of the Coma cluster is of the order of 10 to the 15 solar masses. So we're dealing with something that looks like the Virgo cluster, but at redshift of around 2.2, 11 billion years ago. And here I'm showing the yellow point distribution of confirmed protocluster members and shows a cutout. And they're basically galaxies. There are only a few pixels across. How much time do I have?
Till you're done. Keep going.
All right. I'll go over that. May run out of time. I'll go over that very quickly. So we're interested to know what will happen to our protocluster. The first question that we can ask is that if our protocluster is relaxed by the time of observation at redshift of 2.3, and what do I mean by relaxed? I thought about that. How can I explain a relaxed versus a non-relaxed system, right? And I thought Black Friday is a good example, right? We have some potential customers waiting outside, say Walmart, right? Behind the doors. They open up the door, they rush into stores, right? And as they rush into stores, they start interacting with each other. Maybe there might be some fights over the TV screen or whatever. And then as time progresses, so time is the key. As time progresses, the system gets relaxed. We see people happily moving around in stores, checking their cell phones, buy whatever that is left. So we go from a non-relaxed to a relaxed system over time. So if you give a non-relaxed system enough time, it will eventually get relaxed, right? And we can ask this question: how much time do we need? How much time does our protocluster need in order to get relaxed, right? We can do some simple calculations. And we think that at least it needs 600 million years to get relaxed. And we believe at redshift of 2.23, this protocluster is likely not relaxed. We need at least 600 million years. In other words, if the protocluster has formed at redshifts greater than 2.8, at least, it would have had enough time to get relaxed. How about the present time? So we are looking at a protocluster at redshift of 2.2, but it has evolved into something over this period of time. We want to know what it has evolved into at the present time, right? At redshift of 0. Our calculations show that at the present time, it's likely a relaxed system. It has had enough time to get relaxed. And we can move on and actually estimate the current present mass of our protocluster. And we did this calculation and we ended up with something like 10 to the 15 solar masses. It's like the Coma cluster. So we have something that at redshift of 2 looks like a Virgo cluster that will likely turn into something like the Coma cluster at the present time. In fact, in terms of the present mass of the protoclusters at high redshifts, this is the most massive object that has been discovered so far. All right, I'll get back to this map that I started with. It's an overdensity map. This has been confirmed in 2015 to be a protocluster at 2.1, the northern part of that. In 2020, we confirmed this section of that to be something real. but there are some overdensities here, potential overdensities, for which we can do a spectroscopy, right? In 2020, we had 4 nights with MassFire again to go after these potential overdensities. In April, we had 2 nights, we got weathered out, we had bad weather. And in March of 2020, we had 2 more nights. And you already know what happened in March of 2020. We had COVID and shutdown. So we couldn't do anything, basically. But gladly, we got some more nights. And in March of 2020, just a few months ago, we went after one of the other potential overdensities in this map. And this is the first time I'm presenting these results, and these are preliminary results. So I want you to take this with a grain of salt, okay? Our initial estimates showed that this overdensity next to our protocluster that can also be seen in narrowband data. First, we spectroscopically confirmed that. And it seems to be something real to what we confirmed in 2020. Something just like that. In terms of the size, in terms of the velocity dispersion, in terms of the mass. So what we have here is 2 Virgo-like protoclusters at high redshifts that are potentially merging together, which is very, very interesting result here. Let me give you another explanation why that is interesting. We want to know if this huge large scale structure here is another Hyperion in the cosmos field. What is Hyperion? Hyperion in 2018, it's been confirmed spectroscopically that Hyperion is a supermassive protocluster at redshift of 2.45. So it's a little bit further back in time compared to our structure. It has at least 7 overdensities that have been spectroscopically confirmed. And the total estimated mass of Hyperion is something like 5 × 10⁻⁵ solar masses. So it's huge. It's a huge, massive structure at redshift of 2.45 in the same field, the cosmos field. And it's huge in terms of volume as well. It covers a volume of about 60 million parsec by 60 million parsecs by 150 million parsecs. How about our large scale structure? We want to know if this is another Hyperion, but at lower redshifts, at redshifts of 2.2. In terms of the volume, we estimated this to be around 40 megaparsec by 40 megaparsec by 180 megaparsec. So in terms of the volume, it's very similar to Hyperion, but at redshift of 2.2. And in terms of the number of confirmed overdensities, we have at least 3 confirmed overdensities in this large scale structure, right? So we're dealing with something like Hyperion, but at lower redshifts. The important question that we need to ask is that finding these huge, massive structures in a small volume of the space like that of the cosmos is very, very rare. So the models of structure formation predict that the probability of finding these massive structures is very, very low. So there are some explanations here. There are either the models that predict the structure formation. There's something wrong with those models, at least at very massive end of that. So that's one possibility. The other possibility is that maybe we are overestimating the mass of these structures observationally, because, for example, in estimating the mass, we rely on some assumptions. Maybe they do not hold, right? And the third answer is that maybe we were just lucky, right? We happened to observe a region of the sky that contains 2 very massive structures, cosmos, and we didn't know about that, right? Interestingly, there was a paper that was published just yesterday in Nature. I'm referring to this paper by Atta et al. 2020. Just yesterday, it was published in Nature Astronomy, describing Hyperion and our protocluster here, and some other potential overdensities in the cosmos field in more or less the same redshift in the content in light of simulations. And I need to read that paper very carefully, but I went over that very quickly. And what they found was that Hyperion simulations predict Hyperion to be real and predicts our structure to be real as well. Out of 50 simulation realizations that they used, 47 of them predicted our protocluster. And the same for Hyperion. For the other two over densities in that same redshift, they didn't find that. So I'm quite happy about that result. It seems to be inconsistent with simulations as well. If you're interested, you can have a look at this paper. That was published yesterday. I guess I'll stop at this point. In the second part of my talk, I just wanted to talk about the role of the cosmic web on the evolution of galaxies. But we can talk about that at another session if there is interest.
Sure. Anybody got any questions? Can we do questions now? Sure.
Are ellipticals more central to clusters like you talk about, and spirals more on the outskirts?
Yes. It has also been found that even in galaxy clusters, the denser regions contain more red galaxies, elliptical galaxies, and less star formation activity compared to the outskirts. And also this phenomenon also scales with the mass of the clusters. For example, if you look at a more massive galaxy cluster, so compared Virgo cluster and Coma cluster. Coma cluster is more massive than the Virgo cluster, and because of that, it has a higher fraction of dead red galaxies compared to the Virgo cluster.
But going back in the past then for one of these clusters, like the distant Coma that you've seen, that would be more spirals than we would expect today.
Absolutely.
Okay.
Most of them are active star-forming galaxies.
Yeah. Okay, good.
In fact, all of them that we found have some sort of H-alpha emission, some level of H-alpha emission, meaning that they are forming stars. And because of that, we're seeing H-alpha emission and oxygen-3 that are coming from star-forming regions in these galaxies. Absolutely.
Excellent. Very well organized. Thank you.
Thank you.
I have a question, Ben, if you can handle it here. One of my dumb ones. I understand now the red galaxies have stopped producing new stars, and the blues are nurseries for new stars. That has nothing to do with the red shift and the blue shift of the light of going away from us. Nothing. It's an all new category, right?
All of them. So redshift and blue shift and the light of them is mostly because of the expansion of the universe, right?
Okay.
Now it has nothing to do with that. Red or blue means that, more accurately, when we say galaxy is red in a certain color, it means that it emits or blue. Say a galaxy, when say a galaxy is blue in a color, say visible minus R filters. It means it needs more light in shorter wavelengths compared to longer wavelengths. And the opposite of that were redder galaxies.
I see. You claim to have, Tom, I'll throw it to you right after one little silly question. You claim to have found, photographed, and analyzed, and I assume cataloged 2 million galaxies. I'm sure you didn't name them all, but do they all have numbers, like the phone numbers you see?
They all have numbers assigned to them. In fact, in the cosmos field, they're just a bunch of numbers, IDs that we assign to them, and of course coordinates. We know exactly the coordinates of right ascension and declinations.
Did you get any in the Hubble Deep Field?
Hubble Deep Field in another part of the sky, region of the sky. It's not.
Oh, I see. You just concentrated. Tom Totten, did you have a question?
I have a question from a YouTube chatter, and it's John Favalesa. He says, Behnam, are you so deep into this subject and so brilliant, I have to ask, do you enjoy just looking at the images us amateurs post on AstroBin? So do you get anything out of the other people posting their pictures on AstroBin? I see that you post your own pictures on AstroBin.
Yeah, of course. Hi, John. Thanks for the great question. Absolutely. That's why I do imaging as well. It's a great hobby, and I enjoy looking at just the images of galaxies. And let me just give you some examples. We already know that very recently, a lot of large planetary nebula have been found by amateur astronomers by taking very deep images of certain regions of the night sky. I've been following some of those on AstroBeam, for example. So we can even do science as a citizen scientist just with amateur instruments these days, basically. And of course, I enjoy looking at the images of all the galaxies. It's not just, it's mostly art, right? So there's some technical aspect to that, taking images, being careful about guiding, calibrations and all that. But more importantly, the processing part of that is the art that I really enjoy. And of course, John, particularly your images that you post, some of them are just incredible. Like the M82 galaxy that you recently showed me that resembled exactly like the Hubble space image that I just showed in my talk.
Cotton, you just sent us a message. You want to read it?
It's
Yeah.
just
Oh, that's the same one. I just didn't know if you guys had chat open or not.
How about our outreach coordinator, Chuck? Are you on screen still? I don't see you. You're not one of the four I'm allowed to see here.
Yeah, I'm still here.
Do you have any questions?
No, great talk.
All right. Well, I enjoyed it. This seems to be one of those talks, Ben, that I'm going to have to see again over again to catch up on the parts I missed. It's like taking notes in the class. Do you teach a class at Caltech?
No, it's just research.
Oh,
I used to teach as a TA when I was a grad student at UC Riverside,
right.
but not anymore. I haven't done that in a long time. It's been all research.
Well, since you got your master's degree at Sharif University in Tehran, do I look like the Ayatollah Khamenei, the guy in charge over there? Don't I look kind of like him? Muslim leader.
He's dead already. He died many years ago.
That's Khomeini. The new guy is Khamenei or whatever. Well,
Right.
I don't want to bring up politics, but listen, you did good. And if you're ever up here, look us up, will you? Because we'd love to have you first Friday of every month. Right now we're online, but we're hoping to open up and be on the campus of the beautiful Museum of Natural History by August the 5th.
And our star parties are the second Saturday of every month.
That's even more. Yeah, you're right.
The museum.
If I end up being there at some point, or hopefully get there. And just let me know if there is interest in that. I can talk about the role of the cosmic web and another time. Just
good. Sign them up.
I'll put you down. Next month, we're going to have an exoplanet expert astronomer from NASA's JPL, Jet Propulsion Laboratory. It'll be Dr. Rob Zellum, and he's going to talk about upcoming NASA missions and the possibility of life on planets around other stellar systems. Thank you again, Dr. Ben Darvish. And the rest of you, thank you for a great meeting. Mr. President, we'll talk to you and others on the screen Monday morning for our SBAU Astro Hour.
Yes. See you then.
All right.
Bye. Thank you.
Thank you.
Thanks, everybody.
All right.
I just want to note that people can re-see this program on our YouTube channel. So look us up at the Santa Barbara Astronomical Unit on YouTube, and you can repeat this program. And if you want to leave any comments there, perhaps Behnam will be able to see the comments that you'll make on this YouTube video, and he might give a comment back to you.
I'm going to watch it again. I'm going to have to several times, but we'll see you next month for Rob Zellum. Thank you. And I guess meeting's closed, Mr. President. You want to gavel?
Have a good one.
All right.